Welcome back to the deep dive. We're tackling something absolutely fundamental today in the world of computer science, sorting algorithms.
Yeah, fundamental is the right word.
Think of it as the digital equivalent of organizing your sock drawer, maybe, but way, way more crucial for making computers efficient.
Indeed. How data is ordered or sorted, it really underpins so much of what software does. Understanding these basic mechanisms, it's key to truly grasping how computer systems function and, why they perform the way they do.
Absolutely. And our mission today is to take a deep dive into one specific sorting method, insertion sort. We've been looking at excerpts from the Hello Algo resource.
A great resource, yeah.
And it gives us a fantastic jumping off point to understand exactly how insertion sort works, its technical quirks, and where it actually fits in the vast landscape of sorting techniques. Our goal here is to really help you get this so it sticks with you for the long haul.
This dive is about building that solid intuition, not just memorizing a list of steps.
Okay, so let's unpack this with the core idea. And the source gives us a perfect analogy to start. It says, insertion sort is, quote, very much like the process of manually sorting a deck of cards.
Right. That image is powerful because, well, most people can relate to that, can't they? Imagine you're holding some cards in one hand, let's say your left hand, and those cards are already in order, perfectly sorted.
Right. They're perfectly sorted, maybe, I don't know, lowest to highest, ace, 2, 3, whatever.
Now, you pick up the next card from the unsorted pile, maybe in your right hand. This new card isn't in the sorted hand yet.
Okay. And your task is to take that single new card and find its exact proper place within the sorted cards you're already holding.
Yeah.
You look through the sorted cards, figure out where the new one belongs, maybe shift some cards over a bit to make room,
Make that little gap.
and then slide the new card into position. Bingo.
Exactly. And once that card is inserted, the cards in your left hand are still perfectly sorted, but now you have one more card in that sorted sequence.
Ah.
The algorithm does pretty much the same thing. It builds up a sorted sequence, one element at a time, by taking from the unsorted part and inserting it into the correct spot in the growing sorted part. You can sort of visualize the array as conceptually split into these two sections, the sorted bit and the unsorted bit.
Okay, so taking that card analogy to an actual array of data, how does insertion sort perform this step by step? Walk us through the process, like how the source describes it.
Certainly. So the algorithm starts really simply. It considers the very first element of the array as already sorted.
Right, because one item is sorted, by definition.
Exactly. A list of one element is inherently sorted. That's your initial sorted hand, just one card.
Makes sense.
Right. Then it moves to the second element of the array. This element is like the first new card you pick up from the pile.
Okay.
The algorithm needs to insert this second element into the sorted portion, which right now just contains that first element. It compares the second element with the first.
And it puts it in the correct spot relative to that first one. So now the first two elements are sorted. Either way they end up.
Precisely. Next, it selects the third element. This is the new base element we need to insert. Now, the sorted section consists of the first two elements.
Okay, so the sorted hand is growing.
Right. The algorithm compares this third element with the sorted pair, moving from right to left through that sorted part.
Okay, like scanning back through the cards in your hand from the highest down to see where the new one fits.
Exactly that motion. If an element in the sorted part is greater than the base element you're trying to insert, the source tells us you, quote, move nums j to the right by one position.
You just shift it over.
You shift it over to make space. That's the core mechanic, shifting elements to the right to open up a hole for the insertion.
Got it.
Yes. You continue this shifting process, scanning left through the sorted part until you find an element that is less than or equal to your base element. Or until you hit the very beginning of the array. You run out of cards to compare against. Once that scan and shifting are complete, you insert the base element into the now vacant spot. This spot will be right after the element you stopped comparing at, or, at the very beginning if you scanned all the way back.
So the base goes into the first position you didn't shift something out of.
Correct. You found its home. And after inserting the third element, the first three elements of the array are now sorted.
And you just keep going.
This process then repeats. You pick the fourth element, insert it into the sorted first three, then the fifth element gets inserted into the sorted first four, and so on, all the way until you reach the end of the array.
So you're always taking the next unsorted element and finding its place within the already sorted portion that you've built up from the elements before it.
That's the fundamental loop. That's the essence of it. The process continues until the very last element has been picked as the base and inserted into its correct position within the first N1 sorted elements.
And then you're done.
Once that's done, the source confirms the entire array is sorted. Mission accomplished.
Okay, here's where it gets, well, really interesting for me. Understanding its performance characteristics. All that shifting. It sounds like it could take a while, especially for, a lot of data. What does the source say about its time complexity? How fast or slow is it?
Right. That's crucial. The source gives its worst-case time complexity as O, N2, big O of N squared.
N squared, okay. And when does that worst case happen?
This typically happens when the data is initially in reverse sorted order. Think about it. For each element you pick to insert, and there are about N1 technically, you potentially have to compare it with and shift almost all the elements already in the sorted section. And that sorted section is growing, right?
Yeah.
Towards the end, it could contain almost an element itself.
So you're doing roughly N comparisons and shifts for each of the N elements.
Pretty much. Doing something that takes up to N work, roughly in times, that leads mathematically to something proportional to N squared operations overall.
O and 2. Okay. O and 2 is often seen as, well, not great, maybe. Slow, compared to algorithms like quicksort or merge sort, which aim for O(n) log n.
Generally, yes, for large data sets. But the source also mentions a best-case scenario that's much faster, right?
Oh, yeah, with that.
Absolutely. The source highlights that insertion sort has a best-case time complexity of O(n), just linear time.
Okay, wow, that's fast. How does that happen? When does it get that fast?
This occurs when the input array is already completely sorted.
Ah, okay, so if it's already done.
Yeah, because, as the source puts it, when the input array is completely ordered, the insertion operation will terminate early. When you pick the next element as your base, you only need to compare it with the last element of the sorted section you built so far.
Right.
If the array is already sorted, this base element will naturally be greater than or equal to the last element of the sorted part.
You compare it once.
You compare it once, see it's already in the right place relative to the sorted section, and boom, you immediately know its place is right there after the last element you compared it to. You insert it without needing to scan left or shift anything at all.
Ah, so that inner loop, the scanning and shifting part, it effectively runs in constant time, just one comparison for each element in this best case.
Exactly. Do that n times and you get O(n) overall. This property, performing much better on data that has some existing order, is called adaptive sorting.
Adaptive sorting, okay.
It adapts its performance to the input's existing orderliness.
What's fascinating here is that adaptiveness is a really key distinction, isn't it? It means insertion sort isn't always dragging along at ON2. Its performance really depends on how sorted the data is to begin with. Data that's mostly sorted will be much, much faster to sort than, say, reverse sorted data.
Precisely. And you can contrast that with something like, say, selection sort. Selection sort has a time complexity that's always ON2, pretty much regardless of the initial order. Because selection sort always has to scan the entire remaining unsorted portion to find the absolute minimum element in each pass. It doesn't get any shortcuts if the data is partially ordered.
I see. Okay, so time complexity. ON2, worst case, but ON, best case, and it's adaptive. What about space complexity? How much extra memory does insertion sort need to do its job?
Good question. The source specifies that insertion sort has a space complexity of O1, constant space.
O1, so like barely any extra memory needed, just a fixed amount?
Exactly. It uses only, as the source says, a constant amount of extra space. It needs space for maybe a loop counter, an index variable like J for the shifting.
And maybe one spot to hold the base element while you're shuffling things around.
Exactly. A temporary variable to hold that base element while elements are being shifted. Crucially, it sorts in place. It modifies the original array directly without needing a whole separate copy.
Okay. If we connect this to the bigger picture, why is O1 space such a significant advantage? Why do we care about that?
Well, sorting in place with O1 auxiliary space is very memory efficient. This becomes particularly important when you're dealing with extremely large data sets. Imagine data that barely fits in your computer's memory to begin with.
Right.
You might not have enough memory to create a whole separate copy of the data,
Right.
or some large extra structure that other algorithms might require.
Yeah.
O1 space means it can work even when memory is really tight.
Got it. Very efficient on the memory front. Okay, last technical characteristic from the source, stability. What does stable sorting mean? And is insertion sort stable?
Right, stability. Stable sorting refers to how the algorithm handles duplicate items with the exact same value.
Okay.
If you have two elements with the exact same value in the original unsorted list, a stable sort guarantees that their original relative order will be preserved in the final sorted list.
So let's say I have two 5s in my list. One was originally at index 3, the other at index 7. So the index 3 5 came before the index 7 for the 5 it after a stable sort.
Among all the 5s in the final sorted list, the one that started at index 3 will still come before the one that started at an index 7. Their initial order relative to each other is maintained.
Okay, that makes sense. And is insertion sort stable?
Yes, the source confirms insertion sort is stable. And it explains how. It says, quote, during the insertion operation, we insert elements to the right of equal elements, not changing their order.
How does that work?
When the algorithm is scanning left through the sorted portion to find where to insert the base, remember? If it encounters an element that is equal to the base, it stops the scan at that point. It doesn't try to shift that equal element. It inserts the base element immediately after to the right of that equal element it just found.
Ah, so the new 5 goes after the existing 5 it finds.
Exactly. This ensures that any duplicates already sitting in the sorted section remain to the left of the duplicate currently being inserted. It naturally maintains their original relative order.
This raises an important question then. Why does stability actually matter in practical scenarios? When would I care if my 5s stay in their original order?
Stability is actually crucial sometimes, especially when you need to perform multiple sorting passes on the same data set using different criteria, different keys.
Like sorting by two different things.
Exactly. Consider sorting a list of, say, students. First, you sort them by their grade level, 9th, 10th, 11th. Then you want to sort them alphabetically by last name within each grade level.
Okay.
If you use a stable sort for the second pass, sorting by name, students within the same grade level will retain their relative order from the first sort. Maybe the first sort wasn't perfectly defined beyond grade, but whatever order they were in, they stay in relative to others in the same grade. More usefully, maybe you sorted by age first, then stably by name.
Ah, so all the 15-year-olds would still be grouped together, and within that group, they'd be alphabetical by name.
Well, if you sorted age first, then stable sort by name second, the 15-year-olds would remain together, and within that 15-year-old group, they would stay in whatever relative order the age sort left them in, perhaps already alphabetical or maybe ordered by student ID. The point is, the second stable sort preserves the ordering established by the first sort for items that are considered equal by the second sort's criteria.
I see. And if you used an unstable sort for the second pass?
If you use an unstable sort for names, the students within a grade level might get arbitrarily reordered based on how the unstable algorithm happens to work.
Right.
You could lose the benefit or structure of the initial sort within those groups. Stability preserves prior ordering among equals.
Okay, got it. That makes sense. So what does this all mean then? We have this algorithm, insertion sort. It has a worst case O(n)(2) time complexity, which, seems like a potential drawback for massive data sets compared to the faster O(n) log n algorithms we hear about.
Right.
So why would anyone choose to use insertion sort? When is it actually the right tool for the job?
That's the key question, isn't it? And the source gives us some really clear answers, pointing to its specific strengths, its mesh. First, despite that O(n)(2) for large N, the source states it, quote, is usually faster in small input sizes compared to O(n) log n algorithms like quicksort.
Okay, that seems counterintuitive. How can a conceptually slower big O complexity algorithm actually be faster in practice sometimes?
Yeah, it sounds weird, but it comes down to overhead. The source explains that O(n) log n algorithms, especially the divide and conquer ones like quicksort or merge sort, often involve more unit operations per step.
More complex steps.
Kinda. They might have more complex logic internally, overhead for managing recursive function calls, or complicated partitioning steps. Think of it like having a really sophisticated machine that's super fast for big jobs, but takes a bit of setup time for each small piece. For very small data sets, maybe n equal 10 or 20 or even 50, the actual number of simple comparison and assignment operations in insertion sort, which are very basic operations, can be numerically smaller than the total work done by the higher overhead operations in an O(n) log n algorithm.
Even though n squared grows faster than n log n eventually.
For small n, the n squared value might still be small, and the constant factors, the actual time per operation, are lower for insertion sort's simple steps. The simplicity wins out for small inputs.
So it's simpler, lower overhead for those small chunks of data. That makes sense.
Exactly. And this practical reality is why, as the source points out, insertion sort is often used as part of hybrid sorting algorithms.
Hybrid, like mixing algorithms.
Yeah. And built-in sorting functions in many programming languages,
Mhm.
like Java's standard sort, for instance. The typical approach is something like this. For long arrays, use sorting algorithms based on divide and conquer strategies, such as quicksort. For short arrays, use insertion sort directly.
Wow. So when Quicksort divides the problem down into small enough subproblems, it actually switches over to using insertion sort for those little pieces.
That's often the strategy, yes, because insertion sort is faster at that small scale. So even the big, sophisticated sorting routines rely on insertion sort for the final cleanup on small segments.
So even the big players use it for specific jobs. It's not just a teaching example.
Precisely. It has real-world application in that context. And the source also highlights why insertion sort is generally considered more commonly used than bubble sort and selection sort, even though they're all 0 and 2 in the worst case.
Right, the other O and 2 algorithms. Why pick insertion sort over those two cousins, bubble sort and selection sort?
Well, compared to bubble sort, the source notes lower computational overhead. Bubble sort relies heavily on swapping adjacent elements if they're out of order.
Okay.
A swap typically involves 3 memory movements. Element A goes to a temporary spot, element B goes to A's original spot, and the temp value goes to B's original spot.
Right, that three-step shuffle.
Insertion sort, on the other hand, primarily uses assignment when shifting elements to the right. Element A moves to position A plus 1. That's usually just 1 memory movement per shift. Fewer movements per step generally means faster execution.
More efficient data shuffling, makes sense. What about versus selection sort?
And compared to selection sort, insertion sort's adaptive nature, which we talked about, is a major advantage.
Ah, right. Selection sort isn't adaptive.
Correct. Selection sort always takes roughly the same ON2 time, regardless of the input order, because it always has to find the minimum in the rest of the list. The source states that with partially ordered data, insertion sort is usually more efficient than selection sort.
Because it benefits when the data already has some structure, some existing order. It doesn't have to do as much work.
Exactly. It finishes faster if the data is nearly sorted. And finally, as we discussed just now, insertion sort is stable.
And selection sort.
Selection sort is generally unstable. So if you need stability, maybe for multi-key sorting, insertion sort is the better choice among these simpler O and 2 options.
Wow. Okay. We started with that really simple, intuitive image of sorting cards in your hand.
Yeah, just shuffling cards around.
And we followed that thread all the way through the algorithm's step-by-step logic, the key mechanism of scanning left, shifting right, and inserting the base element, and deep into its technical characteristics: time complexity, space complexity, stability.
We've seen its O and 2. Time complexity isn't the whole story, not at all, thanks to its O and
Yeah.
best case, and that really useful adaptive nature.
Right. And we've understood why its O1 space complexity sorting in place is so valuable, especially with memory constraints.
And how its stability is achieved by that careful insertion process,
Yeah.
always putting equals to the right.
And we've pretty firmly established why, despite faster ON log options existing for large datasets, insertion sort remains a genuinely valuable tool in a programmer's toolbox.
Absolutely.
Particularly for smaller tasks, crucially inside those hybrid sort implementations, and maybe when its specific strengths like adaptiveness or stability are exactly what you need for a particular problem. It's definitely not just a historical curiosity. It has practical applications today.
Well said. Hopefully this deep dive gives you, our listener, a really solid picture of insertion sort that you can hold on to and really understand from the ground up.
Thanks for joining us on this one. It's truly fascinating, I think, how can actually be the optimal tool for specific jobs.
It really highlights the importance of context, doesn't it? And that raises an important final thought, maybe. Since even a seemingly slower algorithm like insertion sort turns out to be optimal in specific common scenarios like small inputs or nearly sorted data. What does that really suggest about the trade-offs we're constantly making when we choose algorithms in software development?
Is there ever truly one single best algorithm for everything? Or is the specific situation, the context of the data, and the constraints always going to be king? Something to think about next time you're faced with a sorting task, big or small.